Hello everyone, welcome back to Electronics 1. Today I want to talk about the other major form of current that we're going to see and discuss in semiconductors. Last class we focused on drift current. This class I want to focus on what's known as diffusion current. Let's start this discussion by looking at another three-dimensional view of a chunk of, well, we'll assume it's silicon again, and let's assume that for some reason that maybe we have holes being injected on the left hand edge of this material, so they're very concentrated over here, and as we move away from the left edge, they become less and less concentrated. Okay, so again, we can clearly see that there are more holes on the left as compared to the right. If we plot this, plotting our hole concentration versus position, so assuming that this is the x-axis along this axis of the material. So if we look at that hole concentration versus x, let's assume that we have some kind of profile that looks like this. Clearly, again, as shown in the figure, there's a much higher concentration of holes on the left of that x-axis, or at we could call it 0 in this x-axis, and as we move in the positive direction on the x-axis, the concentration decreases. This plot can be, we can make conclusions about the concentration gradient from this plot, where the concentration gradient is a function of the slope of the concentration versus distance. In this case, the concentration gradient is negative, right? Because we see a negative slope. Right? This particular snapshot of concentration is not a stable situation. Okay, you may recall from some chemistry class that when we have differences in concentration, there's a tendency to want to equalize that concentration. Okay, so in fact, the natural tendency in any material is for the concentration gradient to go to 0. Or in other words, we have a constant concentration throughout the material. Okay, as that happens, as this concentration gradient results in this desire to reach a concentration gradient of 0, or a constant concentration throughout the volume, we're going to in this particular case, where the difference in concentration is due to charge carriers, we're going to have charge carriers, again in this case holes, that are going to have a tendency to move from the left to the right. And this is to establish an equilibrium where we have a uniform concentration throughout the material. So where the material, the movement is in an attempt to create a uniform concentration throughout the material. Okay, here we have movement of charge, and as suggested in the introductory heading on this lecture, this process is known as diffusion, and that movement of charge is known as diffusion current. Okay, let's present a law known as Fick's law. It's actually technically Fick's first law. And this law says that the diffusion flux is equal to the negative of a diffusion constant times our concentration gradient. So this term representing a diffusion flux, you'll sometimes see this diffusion flux represent, well, I guess we'll look at it here in a second. So, or this diffusion constant, sorry, we'll pull out our fundamental unit of charge out of that. Here's our concentration gradient. And flux, like the flux that we've talked about before, we've talked about magnetic flux back in the past in 1813, and this is kind of the same kind of idea. It's the amount of substance flowing through an area, through an area in a second. Okay, so if referring these ideas to our whole concentration up above, or our whole concentration gradient, that we showed in the block of silicon that we started with, the concentration gradient is due to a difference in concentration of holes. So here we're going to have holes that are flowing with time, which, as I said, if we think holes are carrying some charge, they're flowing with time, then we're can call this a current. And this is our diffusion current. So using Fick's first law and expanding upon it, we can talk about, the diffusion constant for holes times the hole concentration gradient, and if we multiply this all by our fundamental unit of charge, instead of talking about diffusion flux more generally, we are talking more specifically about current density. Okay, so the J representing current density again, the P here meaning this is specifically current density of holes. We have our diffusion constant, but again in this case specifically for holes. Here we have our concentration gradient, but specifically for holes. Say hole concentration gradient. Okay, and we could go through and make all the same argument for electrons that are experiencing a concentration gradient and come up with a current density for electrons. So the equation looks very similar, except that the negative term disappears just because with respect to our normal convention for flow of charge being conventionally assumed to be the flow of positive charge, the flow of electrons is negative charge moving. That negative direction is going to counteract that negative term that was in our current density expression for holes. Just a bit more discussion on this diffusion constant term. Just out of interest, you might note that from Einstein's relationship, we see that our diffusion constant is a function of mobility. Okay. Einstein's relationship says diffusion constant divided by mobility is equal to our thermal voltage, and we remember previously that our thermal voltage was equal to our constant times T divided by our fundamental unit of charge, where that constant term was Boltzmann's constant. And so again, just the takeaway here is just to note the relationship between our diffusion constant and mobility. Not surprising, I don't think, that mobility is going to have an impact on our diffusion and hence our diffusion current, our diffusion constant, and hence our diffusion current. Okay, so we'll leave that topic there, and as promised a couple of lectures ago, this next topic we'll have a look at what happens when we start doping our semiconductor materials, or in other words adding impurities into our semiconductors.